Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, every week we profile some of the most amazing developments in science technology that touch our lives and change the way we see the universe. And speaking about the universe, perhaps the strangest object of the entire universe are black holes. That's the stuff of science fiction, you may think, but no. With us today is Professor Jana Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, and she has a new book out, Black Holes Survival Guide. So we're going to talk about whether or not you can survive a black hole. So first question for you is, how did you, as a youth, think back to when you were a kid? What got you interested in science?
You know, it's funny. I really wasn't that kid who identified as a scientist. Although in retrospect, I had all the signs. I definitely remember staring out my window into the sky and speculating about what was out there and trying to figure out what it meant that the Earth was round, like when I was very little. At one point, I had a very failed theory of cosmology that when I heard the Earth was round, I thought it meant we were inside the globe, kind of like the Truman Show. And so I always was asking questions and theorizing about the world, but I don't know. It didn't occur to me that meant I had a scientific leaning, and now I understand that that's exactly what that is.
So what steered you in the direction of hard science and eventually, of all things, physics?
Well, I came to college and I thought I wanted to be a philosophy major. I was interested in the big questions. I was always kind of reveling in the big questions and the unanswerables. And it took me by just studying the curriculum and in college to realize, actually the way to answer these questions, no knock to philosophy, is really through physics. And I became completely enamored of physics very suddenly and completely unexpectedly. And the math I actually very much like. I really enjoy doing math, and I think I was so kind of insecure because I came to the subject so late, and so here I'm studying physics, and all of my peers had been doing this since they were kids. They always knew that that's what they wanted to do, and so I felt incredibly behind. I didn't know even the most elementary things, and I didn't have a very powerful physical intuition, and so I kind of overcompensated for becoming much more mathematical, just really leaning on the math and what we call, as you know, Michio, what we call following the chalk. And that gave me much greater confidence in the work when I could calculate from beginning to end. I could watch ideas die on the page because the math told you they were not viable. So that happened for me quite late, but when it happened, it was a kind of intense passion for this unbelievable subject that I had completely misunderstood my entire life as a student.
Now, I remember when I was a student learning physics for the first time, there were very few women in my freshman class, and every year there were fewer and fewer women. And by the time I was in grad school, there were no women at all. So did you find that intimidating, or how did you react to the fact that you were probably surrounded by physics nerds?
Well, that was uncomfortable. It was awkward. I can't say that I really understood that, and I have a kind of maybe unusual attitude towards discussing the issue of gender in science because I feel it's something. For women who go into science, it becomes this anvil around their necks that they constantly are asked, or there's pressure within the community to become a social theorist, to become a theorist on gender and science. And there are entire departments that do things like this. And they were not my department. And all of my reflections on being the only girl in the room, which went on for most of my career, were anecdotal and personal. And so I kind of ended up developing a policy that I don't discuss that at least not publicly. I might discuss it personally. And I don't discuss it publicly because what happens is I never escape it once I do. Once I start talking about what it's like to be a woman in science, that's all anyone ever wants to talk to me about. And that I don't feel I'm a scholar in the subject. I don't have all the data, all the understanding, all of the political theory and the social theory. I just want to get out there and to talk about what I do know and what I do well, much better than that, which is physics. And when I kind of implemented that policy, which was very young, people did start asking me just about physics. And I really believe that that's allowed me to have a much bigger impact on both young girls and young boys than it would be if I merely dug into the anecdotes of my particular passage through what was, I will admit, a very difficult experience.
Okay, well, let's just jump right into your book. The book is called Black Hole Survival Guide. And you may ask yourself a simple question. How can you survive a black hole? People think that's the ultimate Roach Motel. Everything checks in, nothing checks out. But anyway, let's back up a few steps. Let's say a kid comes up to you and says, could you give me a definition of a black hole? Just in a few simple sentences. How would you define a black hole?
I would say that a black hole is not an object. It's not a thing in space-time. A black hole is actually a space-time itself, and it's an empty space-time. It's one in which the curves in space-time are so strong that there becomes a point where nothing can escape, not even light. So when we discuss the black hole, what we really mean is that shadow cast on the sky by this region within which nothing is escapable.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today is Professor Jana Levin, Professor of Physics and Astronomy at Barnard College of Columbia University and author of an exciting new book, Black Hole Survival Guide. And you may ask yourself a simple question. How do you survive a black hole? I thought they were supposed to gobble up everything in sight. Well, buy a copy of the book and find out. Well, headlines were made just a few years ago when astronomers announced that they had photographed a black hole at the center of a galaxy called M87. But some people scratched their heads and said, now, wait a minute. I thought black holes were black and therefore invisible. So how can you photograph something that's invisible? So did they really photograph a black hole or something that a black hole creates when they made that announcement, a photograph of a black hole?
Well, what they really photographed was the shadow of the black hole. So imagine taking a photograph of the shadow of a tree. It's not totally dissimilar. To have a shadow of a tree, you need light to cast the shadow. And in the case of this spectacularly huge black hole, 6 billion times the mass of the sun, 6.5 billion times the mass of the sun, in M87, what they have to their advantage is that there's material orbiting the black hole very, very, very close to the event horizon, this region beyond which not even light can escape. And so as this material is swirling around, it's actually quite hot and very bright. And imagine an orbiting disk of hot debris, kind of like Saturn's rings, but more active. It would not cast a shadow for you, except for the fact that the black hole bends the path that the light takes, so that even though this is a disk, it appears, it gives the illusion as the light emanates from the disk, it is forced on a path that bends around the black hole both above and below. So it creates the illusion that the black hole is surrounded by light. And that little detail is what allows you to take a picture of the shadow cast by this bright material. And again, it is like taking the photograph of the shadow of a tree. So that's what we saw, and it's very close to the event horizon. We saw exactly that. We saw nothing. We saw a shadow where there could have been a bright object. And the reason we call it a black hole is not just because the shadow cast is exactly what we anticipate. It matches exactly what was predicted. but that it is so incredibly heavy, but it's only a few times the size of a solar system. And that is staggeringly small in spatial extent. And that's the trick of a black hole. It's heavy, but it's small.
Now, if you want to see the vicinity of a black hole, not the black hole itself, you can look in the direction of a constellation Sagittarius tonight. And in Sagittarius today, there is a black hole 2 to 4 million times as massive as our sun. And so then the question is, why can't you see that black hole? And does that mean also that there are black holes perhaps lurking in almost all the galaxies in the universe?
Yeah, so as you said, in the direction of Sagittarius, we've named our black hole in the center of our galaxy Sagittarius A star because that's where it is from our point of view in that direction. Sagittarius A star, as you said, is millions of times the mass of the sun, but it is less than 20 times the width of the sun across. Think of how staggeringly small that is. Taking 20 sun widths, but jamming in millions of times the mass of the sun. And so it's very small, and it's 26,000 light years away. That makes it incredibly difficult to see. The Event Horizon Telescope project, which made this announcement, had to devise a telescope that was effectively the size of the globe by having observatories around the globe work in concert. And they liken the accomplishment to resolving the piece of fruit on the moon. That's how accurate the observation had to be to see such a tiny object so far away. And another way that they expressed it is it's like reading the date on a quarter in San Francisco from New York City. So it's actually very difficult to take pictures of black holes, and we did not, the Event Horizon Telescope has not returned a picture of Sagittarius A star because it is still difficult to observe, although they're working on it. The likelihood, you asked the second question, which is, are there these supermassive black holes in the centers of nearly all galaxies? And we believe that, yes, that's exactly the case. That means that there are hundreds of billions of supermassive black holes in our observable region of the universe.
Now, it turns out that some black holes can be the size of large stars, and some of them can wander. And some people have conjectured that there are wandering black holes in the Milky Way galaxy, in which case maybe one day we're going to be caught unawares. A black hole will sneak up behind us and basically gobble us up. So what are your thoughts about black holes the size of stars that wander? And will our sun become one of these black holes, or is our sun simply too small to become a black hole?
Our sun is definitely too small to naturally become a black hole. If some evil genius comes along and figures out a way to force our sun to collapse, our sun would only be 6 kilometers across as a black hole. It would be smaller than a city. Most black holes that form naturally by being very massive, collapsing under their own weight at the end of their life cycle, are in the tens of kilometers across range. And so they are, again, very small and very hard to detect, but what we do is this trick called microlensing. So if a black hole were to pass between our line of sight and a cluster of stars, it would make them twinkle. It would distort the image because it bends the path that the light takes to us. And so this little trick of microlensing allows us to look for black holes so that we're not caught unawares. And but there are most certainly black holes that are just freely wandering around the universe. We know, for instance, in the center of the galaxy, around that supermassive black hole, that there may be tens of thousands of smaller black holes just in wild and unpredictable orbits around that supermassive black hole. And then there, where we are, which is in the safer area of the galactic arms, there certainly are some that have been lost to their solar systems and have been ejected and are wandering around. The funny thing about black holes is that they're not these weapons of complete destruction that we make them out to be. They actually have to come really, really close to us to pose a problem. So if the sun were to become a black hole tomorrow, our orbit would be fine. We would not suddenly be vacuumed into that black hole. I mean, it would be apocalyptically cold and it would be dark and civilization would end, but our orbit would be just fine. So that black hole really has to be right on target to hit us, and that's just incredibly unlikely.
Okay, now you mentioned that the Earth is not going to be sucked into a black hole anytime soon. That's what kids want to know the answer to.
Yeah, but we will be eventually.
Well, we are outside the event horizon, which you've referred to a few times. So what is the event horizon? Is it the point of no return?
Yes, exactly. So the event horizon is really a region in space. So many people have heard the story. A very heavy star collapses at the end of its life cycle and begins to enter its death state. And as it collapses and gets denser and denser, there becomes a point where the escape velocity from that star exceeds the speed of light, and that marks the event horizon. Now, Sir Roger Penrose recently won the Nobel Prize just last month for the work that he did that proved that that star keeps collapsing. It cannot sit there. If you go up to this region, this event horizon, and knock, there's no surface there. There is nothing there. And I love this chapter in the book where I just am emphasizing black holes are nothing, because that star that formed it continues to fall catastrophically in the interior, and it leaves behind, like an archaeological record, an imprint on space-time of this location where, if you veer that close, the curves in space-time are so strong that you could not escape. But there's nothing there. There's no line drawn in the sand. There's no matter there anymore. The star is gone. So the event horizon is really an empty region of space-time. And that's why I refer to it as a shadow. You can only expose the event horizon if you illuminate around the black hole, and then you can see, oh, look, there's this dark shadow cast, because in this region of space-time, nothing can escape.
Science Fantastic with Professor Michio Kaku. With us today is John Levin, Professor of Physics and Astronomy at Barnard College of Columbia University, author of a new book. The book is called Black Hole Survival Guide. Now, when we last left off, we were talking about, well, what happens if you fall into a black hole? This has been done, of course, by Hollywood many times, but tell us now about the physics. What happens in slow motion as you fall into a black hole?
If we only consider gravity and we ignore all of the quantum aspects of matter, the matter that actually falls in, and in fact the quantum aspects of gravity. And that story, again, going back to Sir Roger Penrose, is actually more subtle than I think people realize. When you are outside a black hole, let's say you're an astronaut in a space station safely orbiting outside the black hole, you think of the center of the black hole as a point in space. But if you're an astronaut who goes on that exploration, once you fall across the event horizon where there is nothing, there's no demarcation, there's no indication it's even happened to you, you might not even know. But once you're on the other side, it's as though space and time have switched places. And you are forced towards what we call a singularity, which is, let's say that star formed, this infinite region of the curvature of space and time, incredibly strong curvatures of space and time. You are forced towards that region inevitably. And this was something Sir Roger proved in this early paper, that it's as though space and time switch places, and a singularity is now in your future. It is totally inevitable, and so you are driven on a path towards this, and once you get closer and closer to the singularity, things become extremely unpleasant. The curvature of space-time is so strong that you feel it differently on your feet than your head. You feel your bones being crushed together because you're being crushed towards this singular point. And it's as though your body would be ripped apart and flayed. It would be a gruesome death, and it would happen very quickly, depending on the size of the black hole, so that you were dispersed into your quantum particles. You also asked an aspect that people thought about in the very early days of understanding black holes, which is, well, that singularity sounds kind of like the singularity of the Big Bang. Maybe I can sew these two kinds of space-time together smoothly, and they can be sewn together smoothly. It's not a prediction that this happens. It's just that the math allows you to do it. And in that, if you do try that, if you do speculate about that, then all of your quantum bits could be blown out into what is sometimes called a white hole, but is effectively a Big Bang. And you would, in some sense, be contributing to a new ecosystem, a new Big Bang, a new beginning, where maybe new black holes form and new planets form and new sentient life forms and emerges and asks the question. So one of the things that I think is really spectacular about that is, if you think about how small these black holes are on the outside, they can be as big as a universe on the inside. I call it like Doctor Who's TARDIS. It's like the ultimate Doctor Who's TARDIS. Here's this object that's small by astrophysical standards on the outside, but on the inside can be enormous.
Well, in 1963, there was a mathematician, Roy Kerr, who looked at Einstein's equations and assumed that the black hole was rotating so fast that centrifugal force kept it from collapsing, and it collapsed to a ring. And as you know, if you fall through the ring, you don't die. You could conceivably fall through the ring into a parallel universe. And so this does not mean a white hole necessarily, but the question is, does this mean that a wormhole can take you to another universe? Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us today is John Levin. Well, when we last left off, we were bordering on science fiction. The question is, well, what happens if you fall through a black hole? Are you necessarily crushed to death? Some people think maybe there's a white hole that you're blown out of the other end as a new universe is creating. Other people say that, well, if you have a spinning black hole and you fall through the ring, it's not a dot at all, but it's a ring, you do not necessarily die. You can fall into a parallel universe. And if you fall in a second time and a third time, it's like going up an elevator. You simply wind up on different planes of different universes. However, this is all, of course, speculation. So tell us a little bit about where physics is leading. All these speculations about white holes, big bangs, parallel universe. What came of these ideas?
Well, so you're describing the Kerr extension, which is, it's very beautiful to draw these maps of space-time where you see them kind of one leading into the other. But I would say a much more contemporary view requires that we think about quantum phenomena. And that has led to ideas that are even more hard to wrap your head about. There are now suggestions that, let's say you fall into the black hole, it would be hard to imagine you surviving the extreme curvatures, even if there isn't a singularity. So let's just imagine you're torn to your quantum particles. There are ideas now that there are wormholes, quantum entangled wormholes, that navigate from the interior of the black hole to the exterior of the black hole. So let's say I look at one of your fundamental quantum particles inside the black hole. It actually is also outside the black hole. And that this is suggested as the source of the Hawking radiation. Hawking famously said that a black hole evaporates quantum particles that it steals from outside in the vacuum. It never comes from inside. It created this whole war between quantum mechanics and relativity. If the particles don't come from the inside of the black hole, what happened to all that stuff when the black hole evaporates and the event horizon is yanked up and there's nothing inside? And so this is one of the resolutions that says, well, actually, the stuff on the inside is the Hawking radiation, and it was navigated there through a series of entangled wormholes, so that even if you are torn to shreds inside the black hole, there is a thin vapor of hope that if I cautiously reconstruct all of the information encoded in that Hawking radiation, that it will carry the details of your demise, it will carry the details of who and what you were, and that in principle, I could reconstruct from this blaze, from this explosion, especially the final radiation, I could reconstruct your experiences and who you are, and even you. So the only way you could survive that experience would be if somebody faithfully tried to reconstruct your quantum information.
Okay, well, let's jump a few steps backwards, okay, and try to break it down one at a time. First of all, Stephen Hawking said that black holes are not really black. They're gray. So tell us a little bit about what is Hawking radiation and what is the status of Hawking radiation today?
So Hawking radiation was so everything that we understood about black holes and general relativity is perfectly correct in this idealized world where we only consider gravity. And Hawking said, but that's not the world we live in. The world we live in actually has quantum particles. It has matter, and matter behaves in a quantum way. And so even though the event horizon is completely empty, it is nothing, it is nothingness, nothingness isn't actually empty all the time. And when we start thinking about quantum mechanics, we talk about the possibility that an empty region of space, can actually froth with possibility of particles popping in and out of existence. That these quantum particles create a very kind of low-level sea or froth, quantum froth in empty space. You wouldn't notice it if you fell across the event horizon. You don't notice it in your room, but it's there. And these particles must come in pairs. They have to come in pairs to neutralize each other. And what Hawking realized is in the case of this happening near a black hole, one particle can land slightly inside the event horizon and the other slightly outside. And in that way, it can permanently separate these neutralizing pairs. It can steal one and leave the other free to radiate in the universe.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today is John Levin. Now, your book talks about a survival guide. That implies that you can survive. But what does it mean to survive a black hole?
Well, a lot of the advice, I don't want to do a spoiler alert of the end of the book, but a lot of the advice also involves surviving just navigating the exploration of a black hole from the outside, avoiding the jets, for instance. If a black hole is surrounded by debris and material and magnetic fields, which it churns up into these dramatic, tight jets, those jets are effectively astronomical ray guns. If you were to be hit by one of the jets, you would be exposed to lethal doses of X-rays and gamma rays with all of the attendant physical consequences. So the jets, in fact, we've seen jets so big that they puncture holes in other galaxies, destroying planetary systems and life in the other galaxies, if there is life in other galaxies. And so black holes can be lethal in more ways than just falling in. So I can't offer advice as to how to navigate even just the exploration. But the only way to survive falling inside would be the way that I just described, if somebody was willing to try to reconstruct all of your quantum information perfectly and reassemble you. Other than that, it is quite clear that once you cross the event horizon, your doom is sealed. So not crossing the event horizon is really the safest thing to do.
Okay. Now, some people say, now that we mentioned the concept of a wormhole, that wormholes may actually take us to the past as well as to a distant point in the universe. Stephen Hawking once jokingly said that time travel is not possible because where are the tourists from the future? And he said that the radiation that you would be exposed to would kill you. Other people have said that in a multiverse idea, radiation is not circular throughout a time machine, so you're not going to get radiated to death, that you can navigate through a wormhole to the past. But what are your thoughts? What are your thoughts about whether or not a time machine is even theoretically possible?
Well, there was a conference organized at MIT in the past for time travelers to attend. So, if you can time travel, it doesn't matter that it was in the past. You just show up when you show up. There are actual examples in straightforward general relativity, the theory of curved space-time, very artificially constructed universes where we see that you could take a path through time that closes, that comes back to the beginning. In other words, you can time travel. One example was proposed by Kurt Gödel, the brilliant mathematician, that if you had a very odd universe that was spinning in a particular way, that he proved that in that universe you could take a path and find yourself, the famous grandfather paradox, confronting your grandfather before your father was born and shooting him. So a lot of thought has gone into these possibilities, and there's some very subtle arguments. One of the problems with that idea is that we are presuming that we have some kind of free will that transcends physical reality, that is not itself bound to the laws of physics. If you find yourself on a path where you go back to confront your grandfather and you shoot him, it'll be the case possibly, for example, that he is wounded but not killed, but he's an angry man. Your father is born. He makes you an angry man, and that's why you went back and shot him. So there's a consistent narrative. It's a kind of 12 monkeys story. And then there are other people who simply believe that there is something, a kind of cosmic censorship that will not allow these things to happen, even though technically they exist in certain models. So my feeling, I'm partial to the complicated grandfather paradox story, that whatever you do when you go back to your past has to be consistent with you being the person who goes back and does exactly that every time.
Well, it seems to me that the simplest resolution is the multiverse idea, that the river of time forks into two rivers. In your river, your grandfather lived to eventually give birth to you, but in this other timeline, your grandfather died and you no longer exist in that other timeline. So the multiverse idea would be consistent with quantum mechanics, consistent with string theory.
So you mean like a many worlds interpretation of quantum mechanics?
Yeah, that's right.
Yeah. That's right. So, right, in the many worlds interpretation of quantum mechanics, where you again have to invoke quantum mechanics to make sense of this, there are these sort of infinite branching, these dendritic possibilities that allow for consistent histories, and that just depends. That argument, the many worlds argument, is still very contentious, although it has many proponents. But it is, in some sense, the simplest interpretation, the cleanest, most direct interpretation of quantum mechanics. But I think what it says over and over again is singularities, the information loss paradox of Hawking radiation, time travel, and the forking in the road. We can't separate quantum mechanics from gravity and understand the world. We need to understand quantum gravity to really make sense of these hard questions.
And speaking about quantum gravity, string theory is, well, what I do. And however, it's still controversial, not proven yet by any means. What are your thoughts? What about the prospect of a universally accepted quantum theory of gravity that would once and for all answer the question of what's on the other side of a black hole, what happened before the Big Bang, and questions like that? What are your thoughts about a quantum theory of gravity?
Well, I work on the consequences of string theory, and I collaborate with string theorists, even though I'm not directly in that area. And I am agnostic on string theory, but I do believe that some of the advances that we have seen are incredibly compelling.
Once again, John Levin is the author of a new book, Black Hole Survival Guide.